Yes, I think I should. All right, so we're back on this one. Like I said, a surface, yeah, the surface that we are looking at right now is an example. Thanks so much, Anaya. What we are looking at is a typical surface. When you look at it, you will see that there are regular points on it from which the surface was generated. Who can see? Who is actually seeing it? Look at it closely. You see. You see these black points on it. Yeah. So those are the points that were used to generate the surface. Okay. Those are the points that were used to generate the surface. So that is basically, you need to use this because you may want to think with it. Okay, that's one of the basic things that we do with every solution. When you come out with a solution, that a decision is made. Are you all right? A decision is made. All right, great. So we can describe all the interpolation methods, okay? And then of course the use of weights, in the determination of the values. All right. That's another surface over here. So this one is also interesting. As you can see, this one is different from the other one, but then again, you can see the points that were used to generate it. There are some high points, and then there are low lying areas. There are areas that are, pretty low. So here are the high points. These are like the tip, like some cone. Are you okay? Very beautiful. 3D surface renderings are always very nice to look at. Okay. All right. So like I said, it's not only the inverse distance weighted interpolation that we can make use of. We can also make use of nearest neighbor. Okay. We can talk about a spline. We can use the spline. We can use trends. Okay. To also do that. So spline and trend interpolation interpolate best fit surfaces to sample point. Okay, so it may not be that accurate as you can see. It just try to find something that will fit it. So there are different mathematical surfaces. Are you all right? So look at your reality and then see which one fits it. That one is quite dangerous, isn't it? All right. But then of course, it all depends on the data available for you. All right. All right. So if we talk about these least squares and polynomials, because it's mathematical. Interpolation is mathematical. All right. There's another one, that trend surface. Trend surfaces are good for identifying core scale patterns in data. Yeah.
Hello, sir.
Yes.
How is this different from a projected surface?
It's different from what?
Projected surface from the Earth.
What surface from the Earth? The word? I can't hear the word.
Projected.
Projected surface of the. Are you relating it to the topic, the map projection topic?
Yes.
Okay. In that topic, the concept is to appreciate how we can look at a projected surface on a flat surface, a round surface on a flat surface. That's map projection. In this topic, we are looking at the surface as it is. Are you clear?
Still no.
Okay. In the map projection topic, we are talking about. Is this Ben? Is this Ben?
Yes.
Okay, Ben. In the map projection topic, we looked at the Earth. We said the Earth is not perfectly spherical. Okay. And we even talked about the fact that the mean sea level can be extended in theory to form a surface called the geoid, and then we can fit something like a spheroid to the shape of the Earth. But the shape of the Earth itself is not like a football. Are you okay? But even if it were like a football, most analysis that we do are on a flat surface. So that is the map projection concept. In this topic, we simply want to represent the surface of the earth as it is. You don't understand this? Ben?
We simply want to, but the line
Represent
broke.
the
I didn't
surface
hear it.
as it is.
As it is.
Yes.
So like, okay, so it's still on the earth, right?
Yes. But it's
So
not
this
the key
one,
word. The key word is representation. When you project representation, in fact, in this GIS course, put one thing in your mind. We are representing reality. Reality
yes,
is things that when you stand at AIT, you see reality. When you look around you, you begin to see landforms. You see AIT, you can't sit in AIT and write a paper on GIS and fail. So the reality is that the surface is undulating, isn't it? Right? Right? The surface is undulating. Do you understand what I mean by that?
yes,
Wait, it's not,
yes, yes.
it's changing, it's going up and coming down, right? Wait, okay, so now,
yes,
in this afternoon's lecture, we are looking at that, how to represent that surface. Whether it is
that's undulating.
whether it is the physical surface of the earth, okay? Whether it's the physical surface of the earth, or whether it is some sort of theoretical surface like temperature surface. In map projection, we're looking at the physical surface of the earth and how it can be represented on a map as a flat, because the map is always flat.
Yes.
Yes. So the two concepts will never be mixed together. But I like it. I like the way you are looking at it. You are looking at it in terms of the shape of the earth, the shape of the earth. Okay, and you are trying to see the relationship between.
It's round.
Yes, the relation between map projection, where we looked at, the projected surface. So you are trying to. I get it. I get it. I know why. I know why.
I'm looking at it in this section. I'm looking at it in this section. Let's say the person picked the points. Okay, so the point is on the earth. Okay, so if it is projected, meaning that, like you said, the more away we the closer we are, the more accurate, and then the further we are, the more it becomes bigger, and then it becomes a little bit distorted. It becomes bigger. So with this one too, I'm trying to relate it to those ones. If
yes, except that this one, very good, Ben. I think you are thinking through what we are doing, and that's good. In this case, we are just looking at it and we are saying, show me the surface, whatever the surface is. Except that this one also goes a little beyond the physical. In the map projection case, we're looking at the physical shape of the earth, which is round, and how we can put it on something flat. In this topic, we are looking at a surface, and the surface can be the surface of the earth, and or it can be a certain phenomenon, like I said, it can be something totally different from the height of a place. So the diagram we are looking at right now, in this diagram, this could be the surface of a place that you can walk on, or it can be just the presence of something. Okay, I'll show you. I'll go online, then I'll show you an example of a surface which is not made up of. Okay, so Ben asked a question, but I didn't mind him. Okay, so now, but I can hear you now. I'm going to show you a surface which is not necessarily the physical earth. Okay. So surface showing wealth people. Okay, so I'm hoping I'll get something for you. Okay. Using to generate surface. Okay. All right. So maybe let me just show you this. All right. Share. All right. So I've just Googled randomly, but hopefully it will help me to make the point even clearer. In this case, all the images you are seeing, all right. For example, this one is England. The one that you just saw, the one on the right, that's England. Because I know how the shape of the United Kingdom. Are you okay? Now, the surface we are looking at could be something. Are you okay? It's talking about the presence of something else. So it's a surface. It's a surface. But it's not the actual physical surface that you know. Are you okay? Maybe it's not the best example. Let me just go back. I don't want to belabor the points. Otherwise, if this doesn't come in the exam, you'll be disappointed. Okay, so let me leave it. But you can actually have a surface that show how rich people are. That's what I wanted to show you. I didn't get a good example. You can have a surface that show how rich people are. And so in that case, for every household, we intentionally increase the height, the building of the height. The computer will increase the height of the building based on their income. So when you see such a surface, you'll be seeing buildings there are a lot of high, skyscrapers at certain places. Meanwhile, that place there's no skyscraper, etc. This is possible, but it's okay.
Oh, okay. So, hello, sir.
Yes.
So it's something like a histogram.
No. In this case, it will be the surface of the
Something
Earth.
like a histogram.
No, not like a histogram. It's like a histogram, but a 3D version where you can see the histogram. The bars are actually standing on places. And you see a histogram. One of the bars is at the seashore. One is at the main road. Are you listening to me? So can you imagine you have such a histogram?
That the surface doesn't necessarily. So meaning that the surface doesn't necessarily have to be on on the earth.
It doesn't have to be it doesn't have to be something physical on the earth. It doesn't have to be something you can even
representation of data.
Thank you. But then it can be associated with a place, a location. For example, we can talk about maybe political affiliations and try every house where you have NDC people, raise the house up in the computer, let it rise. Extrude it, not let it rise. The word is extrude. Extrude the house. So you end up with a visualization in 3D that shows buildings that are high and colored blue. That would be probably MPP, and colored yellow, maybe NDC. Are you with me? And so you've created a surface, but the values are not based on height, but based on another thing. Are you with me? Another attribute. Are you good?
Yeah, now understood now.
That's good. Yeah.
Can you think about something like maybe the COVID cases, like case rises in Africa?
Yes.
Representing it like in
Yes, you can do that. So in that case, where there's no COVID incidents, it will be flat. The surface will be flat. It won't rise. It will be like low line. Then areas where the COVID is high, you realize that you have a mountain. Are you okay? You'll be having a mountain, exactly. You have plateaus and all that. It's like, and it's very good for convincing people to take an action if you're able to present data that way.
Yeah. When is that pictorial?
Exactly. It gives you that. In fact, it's very powerful. Yeah. These days, cartoons, movies that are 3D movies. Most 3D movies, if you go to box office and you check box office, like I think they keep a value of movie value, the worth of every movie, how much it spent and how much they made. If you go and check 3D, You'll be shocked, millions dollars. And remember, it's 3D rendering. Are you okay? Every movie which is 3D is 3D rendering. Yes.
Avatar was the best.
Say
Avatar
again.
what?
Okay.
You said?
Avatar. Avatar is a 3D projection, and it's one of the highest
Yes,
earning
yes,
movie
yes.
ever.
You can't afford it. You can't even. But so people are becoming rich from doing some of the things I'm talking about. What I'm talking about is like money, But it will take someone who knows what I'm talking to say that, hey, what he's talking about is real. Are you okay? People are making money from 3D renditions and all of. This is the new economy. The economy, agricultural economy, and those things are past. They are like 1940s, 1920s. Yeah, doing agric. People don't have any agric, no corn, but they have the money. They can come down to Ghana now, buy 4x4s and start telling everybody to do what they want to do. Are you with me? So the new way to go is to use data and analyze data, generate new data. In this case, surfaces are new data. Are you okay? From sample points. Yeah. All right, guys. I'm happy you are following it. All right. So here, the surface here is very flat, it's relatively flat compared to the other ones. There are a few protrusions, okay? And this may not be a surface at all. It may not be something on the ground, maybe, but then we can associate it to a certain geographic location. All right. So we can generate density surfaces. There's something called kernel density. When you use kernel density to generate data, for example, if you take crime data and you apply kernel density to it, you now generate mounts. It look like, areas where you have high mountains, it means there's a lot of crime going on there. Kaswa or something like that. Kaswa is becoming very notorious. Are you okay? Yeah. Associated with notoriety and crime. Yeah. Line density, point density, all these can be generated with software. All right. So here we have points, raster, then we have a line overlaid over a density surface from line density on the right hand side in this case. All right. All right, let's keep this bit. Yeah, can be done, but I don't think we should spend too much time on that. Triangulated irregular network. I think we already talked about that. Slope aspects, let's talk about these ones, maybe hillshade surfaces. So a slope tool, let's say you want to generate a slope tool, a slope surface, all right? This is what you do. You put in a DM. Let me tell you what a DM is. A DM stands for, I don't know if I've already said it, I probably have, but I'll repeat it again. A digital elevation model. It's a raster. Are you okay? The raster surface in which the values are actually heights. So DM. Right, so that's what you are actually looking at down here. This one. This is a DM, and then from that DM, you can actually generate a surface looking like, a mountain, isn't it? Okay. But in this case, elevation is in, once you talk about slope, elevation, right? Calculate what is a slope to that. When you do slope, it will calculate when you have a slope surface, you get a maximum rate of change from a cell to its neighboring cells. Rate of change. So when you are doing, anybody who is interested in hydrological analysis, you need to start following this bit, very, very well. So the cells contain values that are actually height values. The cells in the raster data, now every value in there represents height value. So here, look at the key. You see that the key is such that we have the black areas are, have lower values, and then the light gray areas close to white have, example is this part here, white, okay, they have high values. So these places are higher than the black. When we have black, that means that it's a low value. Okay. So this is how DEMs work, but DEMs can be used to generate the slope values. Okay. So now let's look at the slope value, slope surface. Slope surface. All right. So here is a slope surface. So in this, we can find values that are actually not the height values. They are actually what? Slope values. How is slope measured? So this question goes to the class. How do engineers measure slope? Class, anybody can answer. Mention your name and answer to your credits. Yes, how is slope measured? In what units do we measure slopes?
This and by ratio.
It's what? By what?
You can use ratio to define your slope.
As an engineer, if you want to tell the whole world, come on TV, and then they said, tell us, there's been an accident, the car rolled on this. What can you tell us about the slope? What value would you be giving? Give us a typical example.
So change in X over change in Y.
And what is that value? What is the unit of that value? When you divided change in X by, what do you get?
Slope doesn't have units.
Yeah, that one. If it's limited, they will cancel out, so it will not have no value.
Okay, look on the board. Look on the board. You see the answer there.
Yeah, by degree.
Okay. We have 10 minutes. When we come back, we close. Is that okay?
But I thought those ones are for temperature.
They are for what?
Temperatures.
No, there are 3 ways. Let me be very, if I'm teaching you now, I'm not lecturing. This is not this right now. I'm not lecturing, I'm teaching. So let me put it on the board. There are 3 ways of measuring slope. You can actually have it one in degrees, not degrees Celsius. Temperature is degrees Celsius. Then you can have it in gradients. I have it in radians. So typically, you can work between 0 and 2 pi. 2 pi. I can't type 2 pi here, so I'll just I'll put pi. Right? Then of course degree is 0 to 360. Okay, but obviously we all know that every slope varies from 0 to like 90. Once you are at 90, either you are truly vertical or you are. So even saying 2 pi is too far. It's like 2 pi is 360, pi is 180, and then pi over 2 is actually 90. So 0 to 2 pi, pi or divided by 2, and then 0 to 90. Okay, you can take your calculator and work out the gradients. Type in 90 degrees and then convert it to gradients. You get the answer. Usually, radians can be obtained by just dividing it, delta y over delta x. In this case, so please go and do your revision on the different how gradients, slope is actually determined. Use your calculator and you'll be fine. So here you can see that the green areas have a slope of 0 to 9. So you go on the image and then you look for green areas. The right hand side is a render, a 3D rendering. Okay, the right hand side image, this one, is a 3D rendering of what is on the left hand side. It's a raster, but it's not been rendered. So the right hand side one looks more like a solid, something you can, it's like a place, it's like a rocky area. So remember that rendering a surface is different from the surface values themselves. Are you okay? All right. So now green areas they're almost flat. Are you okay? They're almost flat. All right. So let me do this. I don't want to really kind of go deeper than I'm supposed to, otherwise you feel it's coming in the exam. So let me just leave it like that. Let's take the red areas. The values of the red areas are actually very steep. Are you okay? They are very steep. So let's look at, so those are the areas that you can easily fall down. So if someone said, so I can ask you a question in the exam, if I decide I'll ask you a question like that. Show me areas where there's a risk of falling. There will be the red areas. Are you okay? Because a slope of 60 degrees, it looks more like, I'm just going to show you, a slope of 60 degrees looks more like this. This is 45, isn't it? So it will be something like this. It's approaching 90. A slope of 0 to 9 is like something like this. And so we can see that straight away, you can set it. My questions are not supposed to be, they are very common sense questions. Let me just say that, let me be honest. Questions are asked, you have to simply say, okay, I get it. If you don't get it, don't answer it. You answer very important. Then you make your references to the notes and you'll be fine. Okay, so slope surfaces are like that. You can take the surface and go to certain points in the image and then tell whether that place is steep or not. All right, we have what we call the aspect surfaces. So I want to talk about slope and aspect surfaces in this lecture. So an aspect surface will now give you the direction of the plane fitted to the slope face. Okay, so aspect surface is interesting. With an aspect surface, you do this, you find the slope, and then you say, where is it facing? Is it facing north, south, west, east, or west? Are you all right? So the aspect of a surface typically affects the amount of sunlight it receives. Is that also? All right, so if your slope is pointing towards the east, every time you wake up in the morning, you'll be seeing the sun. All right, so it looks like this. So here, when you see a color which is ash, it means the place is flat. All right. When you see a color that looks like mauve, it means you are pointing towards the north, somehow between west and north, so northwest. So these areas, for example, are actually pointing towards the north. Are you with me? It means anybody who is going toward in the northwest direction at a point will see you. Okay, all right. And then on the right, we have the rendition, and on the left, we have the surface with its values. Okay, and so aspect raster is like that. So here the values are, look at the values carefully and tell me what the values are. Christian, I have some friends in the class. I'm making friends. I have Nanaya, my friend. I have Ben. They are always contributing to the class. That's good. It's good to know that. It's good to know some people, isn't it? Wait, they always kind of nice to you. Okay, so what are these values? Please, can you look at these values and tell me what they are? Look at them closely, critically, not closely, critically, and tell me what these values really are and whether they support what I'm trying to describe, the aspect surface, an aspect surface. Look at the values from flat to north. Tell me what are they? Every engineer, let me give you one tip. If you are training yourself to become an engineer, know values. Know that this value isn't all right. No distances. No, I get what I'm saying. That's a good engineer. You can hands-on, you can just say, okay, that is too much, that's too high, that's too low. And based on value. What are these values? What do you think? I think there is self-explanatory. Self-explanatory.
So we are coordinates.
No, they are bearings. They are bearings. They are bearings. Okay. Yes. But thank you very much. They are bearings. You can see that bearings vary from what? 0 to 360. So if you look at them closely, 0, 22, 68 goes then it comes to 360, which is where the north is. Are you okay? All right. So in fact, if you had worked the value 360 and then you knew what the north is, you would have just gotten it. All right, wait. So, and when an area is flat, why is it that we can't give it a direction? This question I shouldn't ask you, but think about it. Go and think about it. Why is it that when an area is flat, the area is not pointing in any direction? Okay. Think about it. We can have what we call a hillshade. So a hillshade actually shows you the intensity of lighting on a surface, all right, given a light source. So the hillshade is like we're creating an illusion, a visual impression, of an area of a surface as if the sun is actually shining. Okay, so let me, without wasting your time, let me show you an example. Example is what we are looking at here. So here you can see that you can clearly see, wow, the sun is shining, isn't it? The sun is shining from an angle. If I walk on this place, I think I can climb up, and the sun is coming from the right hand side. I get what I'm saying. So this is the idea. Okay, guys, so we continue. Let's finish with the next session. It's all right. We are finishing the lecture. The next session, please. Let's join for the last time. And if you have any question on surfaces, also get it ready. I'll just talk about view shed. And then I think we just say goodbye. Okay. So please get any question you have to ready. I'm going to talk about one application of surfaces, and then we say goodbye.